We are talking about electronic transport properties in metals, and in previous times we talked about the Drude model. Basically, Drude model is the simplest model to describe for electronic transport, and Drude model deals with that electrons are single particles. Electrons are particles, and the electron scatters with each other, whether electron-electron interaction, whether electron impurity or imperfections can interact with each other, and this kind of interaction can be treated as a ballistic scattering. But in Boltzmann transport, Boltzmann transport deals that electronic distribution of particles, and the distribution of particles. And here, therefore, the distribution function, the Boltzmann transport defines that the distribution function for example, distribution function with R, and the distribution function measures number of carriers, and mm, measure the number of carriers in the kth state in the neighborhood of R. And in classical statistical mechanics, we know that there is a Maxwell-Boltzmann distribution function, and one representative distribution function is that Maxwell-Boltzmann distribution function. Maxwell-Boltzmann distribution function is a function of velocity, and it is proportional to the. I write down the Maxwell-Boltzmann distribution function m over 2 pi kbt to the 3 half, and v square exponential minus mv square over 2 kbt. It is a Maxwell-Boltzmann distribution function, and it says that there is a particle distribution as a function of v, and here there is like this, and there at some temperature, with a given temperature, at finite temperature, there is a maximum distribution function. This is maximum distribution can be defined, can be depicted, but at finite temperature, also very high speed of particles, or the low speed particles can coexist, and therefore this particle distribution function describes the gas system, ideal gas, described by the Maxwell-Boltzmann distribution function. But here, and I will say that the Boltzmann transport equations, the number 4, for example, is Boltzmann equations, and here here we describe for the distribution time dependent distribution function, and here we define that distribution function in the case the state in the neighborhood of R, and there are several external forces. One is that diffusion. The first one is the diffusion. The diffusion is the driving force of diffusion is the different chemical potential, and the chemical potential is that For example, it is free energy with respect to the number change. And let's consider that there are two rooms, and which is separated at first. And in this case, there are so many particles, or so many children in the kindergarten in the first room. And in this case, the chemical potential is very high. But when you open the door, in some cases, when you open the door, if these particles or the children go into the empty space, and the particle increases. Here, the first room is the chemical potential is very high, and the second room, the chemical potential is very low. Therefore, but there is a chemical potential difference, and therefore the chemical potential difference makes that the particle diffusion. In this case, then particle diffusion, when we consider for the distribution function, the distribution function varies with time. Therefore, we define that the time derivative of a distribution function for the diffusion case. In the diffusion case, it is diffusion depends on the R. Therefore, and it can be write down as that the minus Vk dot partial Fk and partial R. And this is a diffusion term. Then it can be proved that, and here let's consider that the particle time derivative of diffusion distribution function is that for time difference, at some time difference, and Fk has a vary, and here the R plus T Vk minus Fkr, and it is with time interval. This is a distribution function. Then it can be write down that 1 over T, and the first term, let's consider for the Taylor series, Fkr plus Tvk, that's partial F, partial R here. And also second term is minus Fkr. Therefore, these two terms cancel with each other, and this term cancel, and therefore the resulting function is that Vk dot partial Fk and partial R. And here, then we can interpret that, we can understand that the time derivative, the dfk and dt, can be write down as something like that, the dr dt and k, the state, or the partial fk and the partial rk. Here, therefore, is minus v dot partial f and partial r. Yeah, we can understand that the first one is the diffusion. The minus sign means that the chemical potential, the driving the velocity, in the diffusion time derivative of diffusion function is that like this. And let me consider that the high distribution function is some R, and there is a chemical potential difference like this, and then the velocity and this term, the direction is inverse. And anyway, and let's consider it is the first one is the driving force is the diffusion, and here second one is external magnetic or the electric field. The driving force of diffusion can be basically it is a chemical potential, and either increase of chemical potential can be made by the increase of temperature or by increasing the number of particles and so on. And the external fields, because we can consider the Lorentz force, and here H bar K dot, it is force is that the first term is electric field, and the second term is the magnetic field V cross H. 1 over C is in the CGS unit, and in MKS unit, C equal to 1. Here C is the speed of light. And here, let's consider the Fk at time t equal to 0, and Fk plus Tk dot is at the t equal not 0, at finite temperature. Anyway, then the field, the minus Fk dot for field is that 1 over t and Fk plus Tk dot minus Fk. Then also it can be write down as k dot partial Fk and the partial k. This is external field cases. Therefore, we can write down that the field Fk dot for field is that here Fk dot can be come from this equation. This is Lorentz force, and also minus E over h bar, and electric field plus 1 over C Vk cross H, and also dot partial Fk partial K. This one is the external field cases. Let's consider this is external force, and this one is for diffusion. Then basically the diffusion and the electromagnetic field then change the distribution function of particles, and the carrier scatters by impurities or imperfections like a Drude model. Therefore, and the third one, we can say that we should consider the scattering. And here, then the total distribution function, the time derivative of scattering, time derivative of distribution function is that the first term is that the diffusion, and plus F dot K electromagnetic field, and plus, and there is a retarding force. Retarding force comes from the scattering. Basically, we do not know the detailed formalism of the scattering, because the scattering is a microscopic mechanism, and it is a black box. But in a diffusion term, the velocity and position can be write down like this, and this distribution function is kind of distribution function came from the statistical mechanics, like in electron case is that the distribution function is the Fermi-Dirac distribution function, and phonons or the photons is Bose particles, and they follow the Bose-Einstein Bose-Einstein function, Bose function, and therefore, and here, but in scattering, we do not know the detailed calculation, and therefore, in a steady state, this the time derivative of distribution function equal to 0, because everything there is no time difference. Steady, it is the definition of the steady state. And it is reasonable, because when you open the door, and the particle distribution in a room can be stable, but just only the some time, and the perturbation of particles disturb the particle distribution function. But as some time elapse, and the particle distribution becomes stabilized, and steady state reaches easily. And therefore, and the final one should be 0, and therefore minus fk scattering times derivative of scattering is that diffusion plus fk dot field. It means that the scattering mechanism, the diffusion of particles and the electromagnetic behavior of particles that makes the scattering. And therefore, when you write down this one, it is that minus vk dot partial fk partial r and minus e over h bar e plus 1 over c vk cross h dot fk over partial k is that it is the Boltzmann equation. We should remember that this equation, there are two terms. One is that diffusion. Diffusion is position derivative, and field is that the momentum derivative. And the first one is that force, the velocity component of electromagnetic field, and the diffusion case is that the velocity. We call this is a Boltzmann equation. Here, then as I said, and the electrons followed the Fermi-Dirac distribution function. Therefore, here it is that here 1 over exponential beta. Beta is the reciprocal temperature, and K minus mu is a chemical potential. Okay, plus 1, it is a Fermi-Dirac distribution function. Then when you calculate this Boltzmann equation, and we know that the energy eigenstate has this dispersion relation, and the chemical potential is like Fermi energy. It's like a Fermi energy at zero temperature. And at finite temperature, the chemical potential can be changed by the thermal excitation term, but in general, the chemical potential can be considered by the Fermi energy. And therefore, Fermi energy can be measurable by the UPS measurement or the XPS measurement, and also electronic dispersion relation can be calculated from the first principle calculation. Therefore, when we substitute this energy term, and the Fermi-Dirac distribution function can be calculated, and this function can have this calculation. Then we can say that the scattering drives by the diffusion or the electromagnetic field. And here, therefore, to solve this equation is very complex, because basically this equation it needs that band dispersion relation, and from this one, then this Boltzmann transport calculation should be calculated by the numerical calculation or the electronic band calculation. Therefore, it is a theoretical computational method should be employed. And here we define that current density is that integrable EVK and FK dk. It is current density, and the energy flux. Energy flux is that integral epsilon k Vk Fk dk. It is that here it is energy flux. Basically, in equilibrium, the scattering equal to zero. In equilibrium state, Fk and zero equilibrium state, in the scattering equal to zero in the absence of external field. Therefore, this Boltzmann equation some needs to calculate the computational method, and there is a famous program Boltztrap, and by using the Boltztrap program, we can use the this Boltzmann transport calculation. In the next topic, we will think about that the magnetic field effect in the Boltzmann transport equation in the next lecture.